Good morning. Welcome to Mathematics with Tom. I am Tom, and today we're going to look at, we're going to make the jump. We're going to make the jump from discrete to continuous variables. Okay? So a discrete variable, well, this is what we've been studying. Discrete variables, these can be counted. Like the number of people in a room. Continuous variables, continuous data is data that is measured. And the importance of that is, and it can be an infinite number of values, an infinite number of values. So for example, speed, when we talk about the speed of a car, that is continuous data. Remember, if a car was discrete data, like say maybe you increased your speed by 5 miles an hour, every time you sped up the car, you'd go from 5 to 10 or 10 to 15, and you'd be like, wham, so you'd be getting whiplash every time you change speeds. So driving would be a completely different experience, but instead it's a continuous variable. So I'd like to start with what we know. We know about discrete variables. Let's see how we can make the connection between discrete and continuous. So here's what we're going to do. We're going to flip a coin. And I know we've been doing this a lot. We're going to flip a coin 4 times. Okay, now if heads pay 50 cents and tails, that's right, you don't want to flip a tail. Tails cost 50 cents. Okay, so let's write down this distribution. So create the distribution. Okay, that's what we're going to do. So let's just think about this. If I was to get so lucky as to get 4 heads, well, that would be, each head would pay me 50 cents. And so this would give me $2. And so I'm not going to be writing the dollar sign. We'll just write 2 from now on, or 1, or whatever it might be. Now let's just say I only got 3 heads this time. 3 heads would be like maybe that I got the first 3 heads in a row, and then I got a tail. Well, the question to you is, how much money do you get from that, or do you pay? Well, notice the first head is worth 50. Second head is another 50. That's $1. But then you get another 50 for a head, so you're at $1.50. But then you have to pay for the tail. So your $1.50 goes down to $1. And that often surprises people if they're not careful. So now we're at $1. Now we could get 2 heads. We could get 2 heads, which would mean we got 2 tails. Well, we would bring in $1, we would pay out $1, and so we would be at 0. Okay, we're almost done with this distribution. The next one is, I'm going to come up here. The next one is, okay, what if I only got 1 head? Well, then I would have gotten 3 tails. Well, the first head, I get 50 cents. Then I have to pay out for 50 cents for the first tail, so now I'm at 0. But then I have 2 more 50 cents to pay out for those 2 tails. So now I'm at minus $1. And our last one would be if everything went wrong and we flipped 4 tails in a row, well, we would be out $2. Okay? Now, let's write this. And next to all these, let's write their the probability of these. Now, I would encourage you to stop the video for a moment and calculate these yourselves. This is just a picture. Put the probability underneath. Count for the number of ways that you can write the word. Then you should have the answers. So pause the video and then come right back. Okay, here we are. So the probability of four heads is 1 out of 16. Probability of three heads is 4 out of 16. The probability of two heads is 6 out of 16. And let me, just for one of these, let's just remember how to find these probabilities. So for example, this one we just did. So heads, the probability of a head is 1/2. Probability of another head is 1/2. Remember, these are all independent. So a tail is 1/2. Tail is 1/2. But then you have to count for the number of words that can be written from HH to T. Well, if they were all unique, they would be 4 different letters. But then we have to divide by our repeats, of which there's 2 heads and 2 tails. So if we multiply all that up, we're going to get 6/16. Okay, so that's how I would as a quick refresher on a simple way to calculate probability. Okay, now let's see. Continuing on, I have to sneeze just a moment. Oh, excuse me. Continuing on, we have the probability of 3 heads, which is 3 tails. I'm sorry, 1 head. Well, that's 4 out of 16. And finally, the probability of 0 heads is 1/16. Okay. Now, we could just put it into our formal table if we wanted. So let's do that. Let's just take a moment and do that. So I've got, let me see, my number of heads. I'll just write it this way. Number of heads. Well, let's see, we could go 0, 1, 2, 3, 4. X is our net. Really, this is an expected value problem, our net. Well, if we had 0 heads, that cost us -2. Then we had a -1, 0, 1. And if we got all 4 heads, we got $2. Okay. And finally, the probability of that. Well, those are what we just found. So the probability of 0 heads is 1/16. Probability of 1 head is 4/16. Probability of no heads is, or 2 heads, I'm sorry, 2 heads is 6/16. Then the probability of 3 heads or making $1 is 4/16. And finally, the probability of 4 heads or making $2 is 1/16. Okay, and there's my probability distribution. So what I would like to do next is calculate the mean and the variance for this distribution. So let's do that. So the mean, here we go. So we're going to calculate the mean. So we're going to calculate mu. Well, mu is going to be, and now we're going to calculate it as an expected value problem. So we're going to be using this bit of data from our table right here. Okay, so the mean is -2 times the probability, 1/16, plus the data value, -1 times the probability, 4/16, plus the data value of 0 times 6/16, plus the data value 1 times the probability of 4/16, plus the data value 2 times the probability of 1/16. All right, let's collect all of these. So I'm going to I notice I have a common denominator. I did that on purpose. And notice now, what do I get? I have a -2 -4. See, then I have a +0, +4, +2, all over 16. Oh, look at that. Notice if you add those up, you get 0/16. So our mean in this case, our mean is 0, meaning 2 heads and 2 tails, or not making any money or losing any money. Okay. Our variance, So let's calculate our variance next. So our variance, let's write that. I think we have just enough space here. If not, that's okay. We'll go to another screen. So our variance then, our variance is we take the data value minus the mean, so minus 2 minus the mean, which is 0. So minus 2 minus 0. Square it. Oops, you know what? I'm going to write it this way just a second. There we go. So minus 2 minus 0 squared times its probability, 1 out of 16. Plus, we go to the next one, minus 1 minus the mean of 0, square it, and multiply it by its probability of 4/16. And then we have plus the mean, or the data value of 0, minus the mean of 0, times its probability of 6/16. Plus, I have a data value of 1 minus the mean of 0, square it, I forgot to square that one, square it, multiply it by 4/16. Plus, our last data value is 2 minus the mean, square it, and multiply it by its probability of 1/16. Okay, we can do this. So our variance, sigma squared, is going to be a minus 2 squared. Well, that's going to be 4, so that's going to be a 4/16. Plus, minus 1 minus 0 is minus 1. Square it to get 1. Multiply it by 4 for another 4/16. Plus, now I have 0 minus 0. I square it. That's 0. Multiply it by 6/16, and I still have 0/16. Plus, we keep going. We have 1 minus 0. It's 1. Square it. Still 1. Multiply it by 4. That's 4/16. Plus, our last term says 2 minus 0, that's 2. Square it for 4, multiply it by 1, that's 4/16. And we have just enough space here. Add all those up, and we have 16/16. Well, that is 1. And there it is. The key takeaway here is that we have our variance is 1, and our mean is 0. So what we're going to do is we're going to go to the next screen, and when we get there, we are going to now, what we are going to do is we're going to make a histogram. Let's make a histogram. So come with me to this next screen where we're going to make a histogram. We're going to make a histogram from this information. So I know I cleared my screen. I might need to go back there, but I'd like you to keep going. You don't need to change your pages there. So let's make our histogram here. Our vertical axis, we'll put those in 16ths. Our horizontal will be our data. So I'm going to put over here, these are in 16ths. So we're going to go 1, 2, 3, 4, 5. Our highest one will be 6/16. Okay. And now let's look at our data. So our data started here at minus 2. Then we had a minus 1. And we have a 0 and a 1 and a 2. Those are our data values. Now notice, let's make our histogram. So let's make our histogram. And our first bar, now remember the class boundaries are going to be at halves. So from negative 2.5 to negative 1.5, and it's going to come up to a height of 1. So our first bar of our histogram looks like this. Okay, our next bar goes up to 4. Well, 4 is right there, so let's come over here. So our next bar is going to go all the way up to 4. Okay. Now I'm just using the information from our probability distribution. Our next bar, that goes all the way up here to 6/16. So negative 0.5 to 0.5, 6/16. Okay, and then the next one, our next bar, when we have data values of 1, that histogram would be represented here. And finally, our last one, remember the dotted lines I just use as a way so I can kind of keep track of where I'm at here. And there we have it. There's my histogram that represents this probability distribution. Now let's do something interesting with this. Here's what I would propose that we do. So this is, I'm going to call each of these rectangles. Here's an area 1. This one has some area 2. There's an area 3. Here's an area 4, and finally our last one would be an area 5. Now, remember that the area of a histogram, or the area of a rectangle, so let's try A1. It's height times its width. Okay. Well, what is the height? The height is 1, or in this case, it's 1/16. Times the width, well, the width is from -2.5 minus -1.5. We subtract those out and we get 1. So 1 times 1/16 is 1/16. Interesting. Let's try this again. Let's take area 2. So again, it's the height of the rectangle times its width. Well, its height is 4/16 high. It has a width of, you can see it's just 1 if you look from -1.5 minus -0.5. Well, the answer, that's just 4/16 times 1, that's 4/16. Let's try area 3. Now, because of the way the histogram is made, let me keep going, sorry. The height times the width. So the height is 6/16. And the width here is also, it's just going to be 1. All of these have the same width. We did that by the way we built the histogram. All the class widths are the same. So the area is 6/16. Next, area 4 has a height of 4/16, has a width of 1. We multiply those together, we get 4/16. And finally, area 5. Area 5 is equal to the height, 1/16, times its width, which is 1, which is 1/16. Wow. Add up all of the areas. This is kind of interesting. Notice this. The sum of the areas, I'll put the AIs. Well, that's area 1. What this means is area 1 plus area 2 plus area 3 plus area 4 plus area 5. Well, if we add all those up, we can see what we're going to get. But we'll write it. That's 1/16 plus 4/16 plus 6/16 plus 4/16 plus 1/16. You add all those up, what do we get? We get 1. Wait a minute. That's the same as if we added up all of the probabilities. And the answer is, you're right. You're right. Look at what just happened here. Now this is so important. Like if you had a flashing screen, this would be a good time for such a monstrosity. So here's what we're going to do. This is the whole key takeaway, is look at what we did. We have written the probability of a discrete event Now what are we doing? We've written the probability of a discrete event as the area of a rectangle over some interval. Some interval. Now that might not seem very significant, but let me show you how you could use this. So now when we look at the histogram, we don't know about the -2 or the -1, but what we do know about is we know about the boundaries. So we know about -2.5 and we know about negative 1.5, and we know about negative 0.5, and likewise 0.5, 1.5, and 2.5. So now, that's a point, 2.5. Let me fix that, 2.5. So now what do we have? Well, for example, if I wanted the probability, I wouldn't talk about of negative 2. What I would say is the probability from negative 2.5 to negative 1.5 is area 1 equals area 1, which is 1/16. Or I could take something else. I could say the probability of, let's try from negative 1.5 to 0.5. Well, those are the rectangles of A2 plus A3. So we would add up the 4/16 plus the 6/16. So that would be a probability of 10/16, and you can reduce that if you would like. So now, look, this is a big step. Remember, now we're taking a linear number, probability, and we're representing it as a two-dimensional variable, area, and that's the whole key here, because one more thing has to happen. Let's just say we did this game again. And instead of 50 cents, we got 25 cents. And we did it again, but we did it more times maybe. So we doubled the amount of times, and then we halved the payout. So now we're doing it. See, this was 4. Maybe we did it 8 times and paid 25 cents. Maybe we did it 16 times and paid 12.5 cents and continued that pattern. Well, just think about in between negative 2 and negative 1 if we were to do that. That we could get to where maybe we could just pay a dime. You just pay a nickel, 1/10, 1/10. What would happen? I'll show you. Say we were just paying a single nickel between these. Well, that would mean that between negative 1.5 to 0.5, that we would be getting 10 little tiny bars inside of here. In that same region, we'd be getting, there's 3. I'm not even going to make it. They're so small. 4. There's 5. 6, 7, 8, 9, 10. We're going to get 10 bars inside of there. Let's say we took our nickel and made it a single penny. Then that means that if I could look inside of just a single bar, I would have 5 more bars. If I could blow this up, make it really huge. Oops, I lost a red one there. If I could make it so big like that, then I could fit 5 more bars inside of each one of these red bars. I mean, you can see that I can't even draw it that narrow. Okay, well, let's come back here. That's the thought experiment. Now, what do we do with it? That's what we want to see. If I can get it straightened out. Okay, I think we got it back in place. And that's the thought experiment. But eventually, the rectangles would be so small that there would be an infinite number of those. And they would just become and if you were to just very carefully connect the tops of each one of these rectangles, and let's do that. Connect the tops of each of these rectangles, you would have a curve that starts to form like this. And as a matter of fact, it would continue, it goes up, it comes back down, it comes back down, and it comes back down. It does the same on this side. This smooth curve that measures the infinite number of possibilities from discrete to continuous is what's called the standard normal distribution. It's often represented with a capital N, meaning with a 0 and a 1, like that. And what that means is the first number here is the mean, mu, and the second number is the variance, or the standard deviation. We calculated the variance. We found the variance to be 1. Square root of 1 is 1. So we also found the standard deviation. And that's where we get the standard normal distribution. In our next video, we're actually going to take a look at how we can use the empirical rule and the standard normal distribution to find probabilities. I hope that helps. Thanks for watching.